Can you spot the difference between two stones being dropped from slightly different heights and two feathers being released near to each other in a river? Even if you can't explain exactly why, you probably have a sense that these two experiments are fundamentally distinct. You see, while the two stones remain as close to each other during the falling as they were before being dropped, the feathers are able to end up separated by thousands of meters as they are taken by the river stream. Even though in each pair the objects were close together in the initial setup, the distance between them evolves in a completely different way. Classically, we call these integrable and chaotic systems. In order to properly quantify such difference to what regards sensitivity to perturbations over initial conditions, Alexander Lyapunov first introduced in 1992 in his thesis what would later be known as Lyapunov exponents. Let's call z the distance between two nearby trajectories of a dynamical system. A Lyapunov exponent lambda can then be understood as the ratio of exponential growth of the distance z when comparing to the initial separation. Now, are there integrable and chaotic quantum systems? The answer is yes, but in a more complicated way. Usually, bounded and closed quantum systems can be represented by an Hamiltonian matrix, which eigenvalues compose the allowed discrete physical energies of the system. In 1956, Eugene Wigner first took a look at these energies from experimental data of nuclear spectra, and was able to say that the spacings between consecutive eigenvalues were incredibly well described statistically if the Hamiltonian was pictured as a matrix with random entries. This observation grew to the idea that random matrix theory can model quantum mechanical systems when they are chaotic. Later, Barry and Tabor added in 1977 that integrable quantum systems should have several spectral statistics surrounding a Poissonian distribution, so that the two classes of systems would fundamentally differ when it comes to finding energies really close to each other. But what about the Lyapunov exponents? Can they be quantum mechanical? Not quite. The notion of trajectories in a system implied the simultaneous knowledge of position and momentum with great precision, but this is impossible in a quantum setup as stated by the Heisenberg principle. So, to overcome this barrier, Asher Paris introduced in 1984 the Loschmidt-Echo M, measuring the sensitivity of a quantum system to perturbations in a time reversal procedure. Picture initial state psi in a quantum setup. Evolve it forwards in time with an Hamiltonian h1 up until delta t, and then backwards with h2 until an identical time interval. The magnitude square of the overlap between psi and the time-reversed state psi tilde gives the so-called Loschmidt-Echo. This superposition of states decays with time as the Hamiltonians h1 and h2 are different. In fact, for small perturbations between them, several forms of the decay can be deduced, considering that the corresponding classical dynamics is either integrable or chaotic. In the latter case, an exciting result was found by Jalabert and Pastowski in 2001, an exponential decay under characteristic timescales driven by the classical mean Lyapunov exponent of the system compatible with the initial state psi. Whenever the phase space of a physical system is composed of different regions of integrable and chaotic behavior at the same time, the quantum manifestations of chaos become more intricate. For the spectral statistics of quantum systems, phenomenological models interpolating between integrability and chaoticity have been formulated, but the majority of the theoretical approaches have failed, and we still lack until today a solid comprehensive description. Regarding the Loschmidt-Echo, the Lyapunov exponent-driven regime becomes harder to spot as the timescales marking out the window of decay become more complex. In fact, there is no study verifying this match in a mixed system yet. With this, me and my supervisors are going to develop numerical algorithms to compute and obtain the spectral statistics, the Lyapunov exponents, and the Loschmidt-Echo of a two-spin mixed system where two spins interact with each other and with a magnetic field. This should allow us to analyze regimes of mixed regular and chaotic dynamics for which quantum chaotic probes such as the Loschmidt-Echo still need further development. Specifically, we want to determine under which conditions one encounters signatures of the classical Lyapunov exponents in the decay of the Loschmidt-Echo, and identify the time and energy scales of the different regimes proposed in the literature. Additionally, we aim to identify chaotic and regular spectral regions of the system and understand the detailed behavior of the distribution of energy spacings in a mixed dynamics frame. Comparing the distribution of the Lyapunov exponents across the classical energy spectrum to the quantum spectral information is also one of our objectives. This is the proposal of my master's thesis at the Instituto Superior Técnico in Lisbon, under the supervision and guidance of professors Pedro Ribeiro, Ruben Mundaini, and Masoud Hoque. You should check them for nice research in the field of condensed matter physics. Thank you for listening to my project, and I hope to bring you exciting results in the near future.